Hello, I'm Michael Gayton. I'm an electrical engineer in the Mass and Force group of the Quantum Measurement Division, and my research interest here is in the advancement of measurement and calibration technologies for calibrating accelerometers and gyroscopes. Of particular interest to me are these emerging technologies based on micro-electromechanical systems. These kinds of devices are integrated in our cell phones and automobiles and autonomous vehicles of the future. One of the ways that we calibrate accelerometers is based on using a device called a Laser Doppler Vibrometer. And what I'd like to talk with you about today is a new advancement that we have for primary calibration of Laser Doppler Vibrometers using Acousto-Optic modulators. A Laser Doppler Vibrometer is an instrument that is used to measure the velocity of a moving object. Basically, similar to how we can hear a change in the pitch of a sound coming from a moving train, laser light that is reflected back from a moving object will have a frequency shift caused by the Doppler effect. In this photograph, we are looking at the primary calibration system that we use to calibrate accelerometers. The Laser Doppler Vibrometer, or LDV, is mounted at the top facing downwards. Facing toward a shaker at the bottom, the shaker is used to create an upward and downward sinusoidal vibration. And this vibration excites an accelerometer that is mounted on the top surface of the shaker. A helium neon laser produces light from the LDV as depicted in red. The light from the LDV is reflected back with a frequency shift caused by the Doppler effect. The LDV system converts this frequency shift to a voltage that is proportional to the velocity of the moving object. So as you can see, the LDV is one of the main components used in the calibration of an accelerometer, and it in turn must be calibrated with a defined uncertainty traceable to the SI in order to calibrate the accelerometer with a defined uncertainty. In the national labs, we're constantly working on improving our calibration capabilities and decreasing our uncertainties. And so here's what the innovation is in terms of this work. The LDV is typically calibrated by what's called a secondary calibration method. And what that means is that the LDV is compared to another device that is the primary method. And this other device is called a laser interferometer. So the laser interferometer has a primary calibration that's related to the wavelength of light, whereas the LDV is compared to the laser interferometer. What we've done here is we've found a way to calibrate the LDV directly, and it's traceable to the unit of time. Here, we are looking at the calibration system that we've developed. It's based on using an Acousto-Optic modulators, or AOMs, to shift the frequency of the light by a known amount using a sinusoidal voltage generator, whose frequency is traceable to the unit of time. We are using two AOMs because a single AOM would shift the frequency of the light well beyond what is useful for our calibration. The first AOM shifts the light down by 110 megahertz in our application, and then the second AOM shifts the frequency of the light up by the same amount with an additional smaller delta frequency shift that we actually want. So the two large frequency shifts cancel each other out, and we are left with the delta frequency shift only. The light is then reflected back from a mirror to return to the LDV, and this doubles the light shifting process and giving us a 2 delta frequency shift. This 2 delta frequency shift creates what we call a synthetic velocity shift due to a moving object that is calculable using the Doppler equation. Here, we are looking at a plot of the velocity reported by the LDV in comparison to the calculated velocity determined by the Doppler equation. This data is generated using a fixed frequency shift at each point, which would be equivalent to looking at an object that is moving either towards or away from you at a fixed velocity. However, we can also use frequency modulation to simulate a vibrating surface. This plot shows a result of using frequency modulation to simulate the shaker. The most interesting result here is that we can not only calibrate the LDV as a function of frequency, but we can also characterize the bandwidth of the LDV as well. So the system that I've shown you here for calibrating the laser Doppler vibrometer is a prototype system, and we are continuing to look at ways to improve it and to make it more portable so that it can be used in the field. I hope you found this presentation interesting, and thank you very much.